Almost done. Couple of more minutes. Okay, I think we can get started. Happy Thursday. Thursdays considered good day. Every day is good, can be good. Okay, so what we had last class, what you learned last class, actually last class was good topic, sequential experiments when you have multiple stage to do something random, like randomly choose one, and then again in another stage take more random, select more, and keep going. This kind of experiments called sequential experiments. When you are talking about sequential, it means time involved, different times. That's why it's sequential. One after each other, step by step. So it was lots of applications. One of the good applications was that street lights, traffic lights actually, that being green in a next intersection can be sometimes depend on the first. You prefer, if first one is green, the next one be green as well, to don't waste your time. So we can design a model to, we can design a system to model these kind of dependencies between different stages. That's called sequential experiments. We talk about how we can demonstrate that using a structured way. One of the method that we explained was a tree with lots of nodes and edges between nodes, between children and parents, of course. And this tree structure can help you to understand how this relationship works. Each edge corresponds to probability or conditional probability, and last leaves corresponding to actually multiplication of all of that path. So that was last class. Still, we're going to work with these graphical models in this class as well, like a tree structure, because tree structure is going to help us to understand, to visualize it. And visualization is one of the important parts in hard stuff, in modeling, when you are dealing with some mathematical stuff that is so complex to explain with word or numbers or formula. It's good to visualize it. That's actually a very good, good way. Using trees, later on we can see how we can model it with graph. Graph is more, we explained last class that graph is more kind of summarized all the tree in less nodes. It's like packed graph. We have different type of graph that we're going to see them later. But what we're going to do today is not important what we're going to do. It's important what you're going to learn. What you're going to learn I don't know. But if you try, and if you be in the class, play your role properly, be a student, and if I be good teacher, you might learn how to do sampling, and also counting. Sometimes you need to count. Of course, you know how to count, but if it's going to lots of numbers, sometimes counting need to be also modeled with a formula. You're going to see that. And sampling is not just always easy to just randomly sample, take something from a bean. Sometimes order is important. You need to choose one by one, and like you are selecting 3 students. That's supposed to be the first, second, and third, person, and we give them different responsibilities. So ordering sometimes matter, sometimes not. And this kind of selection is different type of sampling, of course. And sometimes we select things and we don't return them back. Like, for example, you are selecting in that example, last class, we had a bin of resistors, and we take some, but we don't take them back. Did we? I think in that example, or we can return them back. So we have different type of way to play with sampling. But this is stuff that I'm talking you already know, probably in calculus 2, or I don't know, linear algebra, something. A permutation, remember that? Yeah, we can see that, or combination. So that's what we want to talk today. It's not that, new, probably you know most of them, but we're going to connect it to something that you don't know to see. Because counting is not the basic of probability. Probability is the base. But counting can be help for knowing this sample space. You need to know sometimes the number of sample space, do you? You don't. You need to know how many sample we can take to make probability. Okay? And it's not always easy. For example, if I say, okay, I want to choose one of person in this class that give, for example, a present, so the probability is just 1 over the number that, I don't know, 75. But imagine I want to choose 3 of them and give them different price. In that case, it matters. And how I can compute probability in this case? We need to see if we take 3 of them, what is the number of sample space if we take 3 of them? So it's going to be like permutation of 3 from 75. 75, yeah, number of students. I don't know, 76 maybe. But that's the idea that we're going to talk today. OK, so now that we set the stage, let's go for counting and sampling. OK, sampling means what? Sampling means selecting. You have multiple things to select, and you select. You select outcomes from population. You have a population of, for example, you have a bin of resistors, and you want to choose 10 of them. Okay, that's called sampling. You are sampled that. And sampling is random. We are randomly choose, If you want to sample, so randomly we are talking about random sampling, of course. However, I said random, but still you need to think. It's Still, there is some distributions. You know, when we are talking about random, still we have distribution of choosing, you know. So we can see them later, but is random. For now, let's consider that random. Why counting matters? Okay, counting matters because sometimes it's hard to count if the number is not limited. But we can summarize counting with a formula. A formula. Like, for example, when I tell you what is as the example that we had, I want to choose 3 of students, how many cases we can have selecting 3 from 75? So hard to list them. If you want to list them, it's going to be a lot of numbers, and count them is so hard, and we're going to make mistake. But with mathematical methods and formula, we can summarize it in a formula. That's called counting. Counting doesn't mean to just count, means to find a formula that shows the numbers. Okay? So that's why counting is important. And again, counting is important because of probability. Probability is always something that we want over all of them. Okay? If you want to choose, for example, you have 52 cards, playing cards, and we want to choose 1. What is the probability to be king? So you are counting, oh, we have 4 king, and 52 is 4 over 52. 52 is all of them. That's why counting matters. Counting is important. And sometimes, as I said, it's hard. Maybe for cards, still you can count them one by one because it's limited. But if the number is going to like very big or very large, it's so hard to count them. It's hard to list them, and it's hard to count them. So it's better to, this formula going to help you. Another thing in counting is sometimes in sequential experiments that we had last class, this counting becomes a little complex. And if you know formula, kind of can help you. For example, let's give you one example here. For example, you have that example of winner. Imagine we have 75. Okay, let's make it 100. This 100. We have 100 students. And we want to choose 3 winner. But it has steps. I mean, different levels. Number, first person, second person. Ordering matters. Okay, in this case, let's see how we can deal with that. Let's draw the graph with this. Okay. Imagine we are choosing from 100 people, 1 person. From 100 students, 1 person. What is the probability of being win? What is probability of being win? 1 over 100. Okay? 1 over 100 is probability of W1. So, okay, if it's win, it's done. If it's lose 1, L1, what is the probability of being lose? 99 over 100, right? Because these need to complete each other. They need to add together and become 1. Okay, if it's win, they're done. If it's lose, it still can have chance to get win again because we are choosing 3 times. Okay, in step 2 is win. What is the probability to be win? In this case, we have 99 samples. Sample space has 99. So we are choosing 1 from 99 and a 98 from 99 to again be loser. That's so bad to be loser second time too. Okay, but we not give up. Still we keep going. Still we have another chance to win 3 and lose 3. Okay, now I ask you, what is the probability to 3 times be loser? Find it. Based off that graph, you can find what is the probability to 3 times be loser. Be loser. Okay, so what we want to find, just going to write it, you're going to compute it, okay? We want to find what is the probability of L1 and L2 and L3. Loser, loser, loser. What is this? So in this graph, you can find it. L1, L2, L3 is this line, this path, this path. Okay? And based off last class, you can break that down to multiply these edges. What is this edge? P of L1. What is this edge? P of L2 given L1. And P of L3 given L2. Oh, it's kind of chain rule, isn't it? P of L3, L2. P of L2, L1, P of L1 is chain rule. But in a graph, we had that last class as well. So they are kind of completing each other, you know. It's supposed to be equal, you know. Whatever we said about chain rule can be proved with this graph as well to be correct, you know. It's math. Even though it's statistics, even though it's probability, even though it's not certain, but it still is math. Why is math? Because of that axioms that we defined. Okay. So that was good. So you can see sometimes 3 doesn't need to be full. This was example. Doesn't need to, because when you are winning, you're going to go home. Don't need to play more in the game. No. But sometimes, if still you are winner, but come back to game again. That's the time that we return back sample to the pool again. You know, we take it and use it and put it back. It's like selecting resistors and return it back to the bin, something like that. We're going to have that next class. But this class, we are just taking and don't return it back. OK, so what about rest? I did that part. So what about this? We have 100 students. We select 3. What is that probability? Oh, we have numbers here, kind of, you know. OK, I just wanted to, what about number in this case? Last one. OK, here we have, because we took 2 off, so we have 98. We want to be lose again. So from 98, we need to probability of losing 97 over 98. OK, this line makes it more complex. So this is for that. OK, so if we put them here and write them up, it's going to be kind of 99 over 100. Because we multiply them, we put them different. 98. I put dot in for multiplication to not make it complex. 100, 99, 98. Oh, that's familiar. It looks like factorial. What about, we consider this 100 factorial over actually 97 factorial. Yeah, no, when 97, put 97, multiply 96, now 95, and so forth, and 100 the same. That's going to cancel out each other. What's going to stay out? This going to stay out. So we kind of proved that. It's not proof, it's just showing that actually this graph, this tree, kind of showing this is permutation. Because we are selecting with order. This is permutation. This is the formula for permutation. We're going to see that next class is n factorial over n minus k factorial. And we can show that with n over k. N factorial, n minus k factorial. Permutation. Same formula, okay? So that's why for sequential experiments that sometimes get complex to count, we can use formula. But you always need to, I don't want you to memorize formula. Sometimes you need to, see this, how this formula coming from, or you can use other methods, like these graphical methods, to verify that. Okay, any question about this? Yes? 97 over 98, that is this one actually, is for this edge, last edge. Okay? Yeah. And when we put these paths together, multiply them together, we actually multiply them like that to become this number. This is actually multiplying this tree part that I just wrote them together. Yeah. But the formula for that is very simple here. Permutation of n, k from n. So we have n is 100, k is 3. So if you put that in formula, the value that going to get is going to be this. I just wanted to show how we found these numbers with showing that graph. Okay. Okay, let I clean this up. So in general, how many total outcome are possible? That's the point that we needed for probability. Principle, like foundation or fundamental of counting. So as you can see, as you saw actually in that graph, last one. Let's see. Okay, last one here. Oh, what happened? They're all gone. Oh, I cleared them. Anyway, in that graph, we multiply them together. We said, okay, in stage 1, the number was this, and in stage 2, the number was that, and we multiply them together. This is what I want to mention here. If we have different stages, in stage 1, you have, for example, 2 choices, and in stage 2, you have, for example, 3 choices, and in a stage, for example, last stage, you have just 2 again. Okay? So if we multiply them together, it's going to be 12, for example. Number of sample space is 12. Why? If you count them 1, 2, it's going to be 12 at the end. Okay? So this is what I mentioned there. If you have different stages, if you have different steps, and in step 1, you have N1 outcome, in stage 2, you have N2 outcomes, and go forth, the number of sample space is coming from multiplication of them. You can see that in that graph too. In first step, you have 2 outcomes. In second, 3, and the last 2. If you multiply them together, it's going to be 12. If you count number of these leaves, they are 12. Good. Okay, example. Okay, let's clear this. Flip a coin, and then roll a die. So flipping a coin, the best way is to just draw the graph. Flipping the coin is going to be head and tail. And then rolling a die. So die has 6 parts. So each one has 1, 2 to 6. 1, 2 to 6. So this has 2, this has 6. So this has 12. So you have 12 cases. So the total outcome is the total number of paths. As you can see in this graph, the total number of paths, this path 1, this path 2, this path 3, this path 6, because I didn't put the rest here, and 7, 8, and 11, and 12. 0 to 12. You have 12 paths, different paths, and each path showing probability of this and this. So probability of, for example, maybe this one. You don't have a space here. Probability of being head and 2 is equal to probability of being head, probability of being 2 given head. Okay? So it's going to be probability of 2 given, this is and, okay? 2 given head and probability of head. Again, chain rule, and you can compute that based off the graph as well. Question? Yeah, this graphical method gonna solve. Sometimes this to understand is so complex. If I just talk in this, you need lots of time to analyze what's going on here. But with that graph, you can understand it better, I think. Maybe you're not that visual. Some people, I'm visual. When I see something, I remember it better. But if somebody tell me something, I'm going to forget it. It's hard for me to listen and remember. But when I see something, I remember better. People are different. Some people have two ways to interact with, environment. Both good. But mostly people, like especially boys or men, are visual. When they see something, they can remember that easier. Okay, so let's go another example. Sequential experiments. So we have flip a coin. Okay, the same problem, but in this case we have what we want to find. Okay, what is the probability that the coin shows head and the die shows even number? So in this case, we're going to change a little bit. Last graph was head and all the numbers. But here we have head and tail. But here we have even and odd. Okay? This is probability of being head. This is probability of being even, given, head, and so forth. Okay? The things that we need to understand, the total theorem in summing this need to be valid. So in these two, P of head plus P of tail need to be 1. In here too, P of even, if the first is tail, plus P of tail, P of odd and tail need to be 1. This is total theorem that need to be valid for each of these two, you know. Okay, so what is the probability? What we want to find? We want to find, okay, so that's the head. So what we want to find is, okay, so we have 3 cases to be even. What? Yeah, if yeah, of course. So okay, this solve that another way, but doesn't matter. We're going to have the same result. So what we're going to find, probability of head and even. Okay, which one of these lines is that? Which one of these paths? Probability of head and even. This one. I'm going to show in another color. This one. We're going to find this one. Probability of head and even. So it's going to be equal, this is the second way to solve it. Even given head, P of head. What is the probability of being head? 1 over 2. What is the probability of being even when it's head? Is just that we have 6 cases. 3 of them is even, so it's 3 over 6. If you multiply them together, it's going to be same numbers, 3, 12, or 1 over 4. I should erase this one, covering that. Okay? So if you understand this part, I'm going to explain that one as well. So based off that graph, probability of being head and even can be computed based off those paths. We have 2 probability, one conditional, one not. We multiply them together. We know probability of head. What is the probability of head? It's just 1 over 2 because we have 2 cases, head and tail. 1 over 2. Probability of, okay, is head. We don't care about the head. And now what is the probability of being even? Because it's a die, and you are you want to see it has 6 sides. So 3 of them is even, so 3 over 6. And we multiply them together, it's going to be 3 over 12 and a quarter. Okay, that was one method that we explained. But let's go back to number space when we want to count, you know, how counting help us. So if we consider all of numbers, all the sample space is going to be like that. In this case, we counted all of them. This is all the sample space. This is sample space. All the sample space. Head 1, head 2 to head 6. Tail 1, tail 2 to tail 6. All the sample space. If we count them, the number of sample space is 12. because it's 2 and 6, 12. Okay, so we have 12 cases. What about, but in this example, we have another choice. We want to find probability of head and probability of even. So in this case, sample space is this: head 2, head 4, and head 6, just 3 cases. And number of sample space, so this is sample space, and the number is just 3. When we put that, means the number. Okay, so we have 3 from how many? 12. So we are choosing 3 over 12. So 3 over 12 coming from this. 3 over 12. But I like the graph one, because you're going to see so many other things here, and you can understand it also easier. Good? Any question? Okay, let's go for how we count without count, using these 2 methods. We have 2 counting tools that can be used for counting. One is permutation, that order is matters. For example, you want to find the example that I mentioned. You want to choose 3 people and give them, I don't know, a gift, but first, second, and third have, they have different gifts. The first is better. So this type of choosing is ordered choosing. So we have ordering. In ordering, we use permutation. We show permutation with this, or in the easiest way, N, K. We also show like that. Sometimes this P is not probability. This is for permutation. Permutation. This P stands for permutation. But don't use P, just use this notation, N, and selecting K over N. When order matters. Okay? How we can prove it? Oh, it's so hard. How we can prove it, that these 2 are equal? Sometimes we can just show it with multiple case, and that's also kind of proving. So let's try to show that. I think we have one example. Oh yeah, we're going to show that next slide. What about combination? Combination is when order is not matters. Order doesn't matters. You have a bin of resistors, and you are selecting 10. Doesn't matter which one is first, which one is not. Okay? So in this case, we need to eliminate some numbers from the big sample space. So the big sample space is permutation. In this case, sample space is a little smaller. Why? Because, for example, register 1, register 2, and register 3 is equal to register 1, register 3, and register 2. Because orders not matters. In the first one is matters. So if order matter, for example, student 1, student 2, student 3, it's not equal with student 1, student 3, student 2. It's different. Orders matter in that case, so the sample space is bigger. In this case, sample space is smaller because we need to eliminate some of them. These two, when these two happen, we say, oh, these two are equal. We eliminate one of them. Okay? In this case, the number coming from another formula that's called combination, combining n from k from n, that is the same way, kind of, maybe I write like that, nk over k factor. This k factor you're showing this elimination. Okay? So the last formula going to come from this n factorial, k factorial, n minus k factorial. I show with different colors to not mix with that. Okay? So this k factorials is this elimination because they are similar. They are equal. We don't count them two times. Okay? We need to see an example. I know it looks a little. Let's show the clear formula. Okay? I talk about this part because this is the part that is not here. So this is smaller than that if k is bigger than 0, 1. If it's bigger than 1, this is always smaller than that because order is not matters. Selecting R1, R2, R3 is exactly similar to R2, R1, R3. We eliminate. This is not considered as a counting because they are equal. Okay, I know. Let's have example. So you have 52 cards, and you are trying to choose 7 cards. And counting, actually order matters. So the first card, when you take, how many chance you have? 52. For the first card, you have 52 chance. Okay? When you take one, you put that in your pocket. No, don't need to put it in your pocket. Just put it away and take another one. Now you have 51 choice. Again, put that away. Don't return it back. And because we're going to go for 7, next 50, then 49 choice, and then 48 choice, and then 47, and then 46. 7. So this is all the possibilities that you can select. Okay, so if multiply them together, the number of sample space choosing 7 cards from 52 cards is going to be 52 product or multiply with 51 all the way 46. I don't know how. And this is equal to 52 permutation of 57 from 52. This is same. It's equal to this. So I'm not talking about probability yet. We are just talking about counting. But why probability is related? Because counting is important for probability. We need to know what is the all sample space size, and we find the size of demand, which one we want, and we divide it by this to find probability. But we are not here still in probability space. We are in counting space, another space, loss of space. Okay, so question is simple. You had that in high school, I guess, or not. You can learn it here, of course. Let I clean this. I have clear version of that, I think. and the formula coming from that. This is general formula. Example. Password is good example, actually. You have, oh, but this is not normal password. Okay, maybe I don't ask. I want you think what's this about. Okay, we have a password that you are probably you saw them in these keypads that you enter. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 probably here. You have this pad, and you want to enter your password, and you have 4-digit password. Okay? So, how many, what is sample space? A number of sample space, of course. What is number of, I don't want to write all the sample space. Number is important. So, how many way you can choose 3 numbers from these 0 to 9. This is 10 numbers, okay? Okay. Any question so far about question? Any question about question? No question about question? But I have one question about question. What's that? Can these numbers repeat it or not? This is the point that you need to consider. Can we put this number 1, 1, 1, 1, or need to be 1, 2, 5, 7? We need to mention that. For the first one, is so complex. We don't consider that one. No. We consider this. So it means digits cannot repeat. Okay, that makes the simple question like solvable, easier. That is solvable too, but it's math problem. It's not really. Okay, anyway, digits cannot repeat. In this case, we are, but is important. This is not equal to, for example, 1, 2, 7, 5. These two are not equal. So the order is important. What is the sample space in this case? I'm saying we have 10, and we're selecting 4. I'm saying it's going to be that. I don't know what you're saying, but we can prove it. Why? Because first you have 10 choice when you choose 1. Okay, maybe I write it here. Okay, and make it more interesting, different color. You want to enter this. How many choice you have? 10. 10 you have. For example, you choose 1. Now you have 9 more, because 1 is gone. You have 9 more choices. You choose 6. Okay, 6 is gone too. You have 8 more choice, and you choose 0. And 0 is gone. You have 7 more choices, and the last one is 7, for example. So we multiply them together, and this is going to make number of sample space. I'm not going to multiply them. You don't need to. Big number. So that's how we find number of sample space if order matters. Order matters. And repeating not allowed. Okay, in this example. Question? Okay, let's clean this. And now see another example. Another example is very simple. Is racing or winning. We have 5 runners, and we choose 3 of them. Oh, it's so easy to be win between 5 runners. So anyway, but order matters. We want to choose first 3 of them and give them prize. And order matters. So this Alice, Bob, and Carol are not equal to, Bob, Alice, and Carol. It's different, okay? So in this case, how many choice we have? From 5, okay, from 5, you had first choice is 5 for selecting first one. You have 5 choices. Select 1. For select 2, you have 4 cases, and for selection, last selection, you have 3. So multiply them together, easy. Okay, let's do one if order doesn't matter. The example, good example, is a bin of resistors that you want to choose 3 of them from 10. You have a bin, lots of resistors here, 10, and you want to choose 3. In this case, order not matters. So in this case, register 1, register 2, register 3 is equal to register 2, register 1, register 3. So we need to eliminate these numbers. How many cases they can? Because we have 3 factorial repeating that we need to remove them. So the formula is actually combination of 10, 3 from 10, that is actually equal to permutation of 10 over 3 from 10 over this number, because it's repeating 3 factorial. That is equal to 10 factorial, 3 factorial, 10 minus 3 factorial. That's it. Okay. So the important part is we eliminated this part. This is the part that we need to take that out because it's similar. They are similar. We need to take them out of the numbers. Okay? Okay, that's any question about this? There is another example. Let's finish that before going. Yeah, we have a little time. Choosing a team. Yes, we have some students, 12 students, and we want to choose 4 of them. And it's not important which one is first, which one is second, how many cases we can have, because 2 things important. Replacement, no, we don't return them back to the pool, and orders not matters. And we need to do combination of 4 from 12. Okay, that's it. This is just summary of what I mentioned. So if you do sampling, 2 cases happen. Order matters or not. First, are you replacing or not? And then order matters or not. For if we replace it or not, we just cover today without replacement. Next class, we're going to talk about replacement. But right now, if you don't replacement, you just have 2 cases. Order, if it's matter, you use permutation. And if order is not matters, you're using combination. And formula given. Next class, we're going to talk a little bit about that, and also going to go for random variables, like real stuff. Okay, have a great day. I'll see you next week. Don't forget your assignment. Every week we're going to have new assignment. Yes.
We're on that second quiz.
Sorry?
There's a second quiz on Canvas that
Yes.
attendance quiz today.
A second quiz?
Yeah, there's a second one on Canvas.
It was on Canvas.
Yeah, there's the quiz that we took at the beginning of class.
Yes.
And then there's a second one That has
Oh.
to do at the end of class. There were 2 quizzes on Canvas.
No, it was just one. Is it two? I confused. Let's check.